We continue with non-dimensionalization, with discussion of non-dimensionalizations of equations of motion. To non-dimensionalize an equation, we need to select scaling parameters based on the primary dimensions contained in the original equation. Number one, it must be relevant to the equation of motion that we are working with. Number two, and obviously it follows, it must have relevance to the fluid flow situation, to the fluid flow problem that we are discussing. So both these things are interconnected. Obviously the equation is also representing the same fluid flow, but in some cases the equation may be representing a more generalized phenomena and will have to be reduced to the fluid flow situation under special conditions. So anyway, we will discuss when we need to do that, but at the moment the important thing is the scaling parameters that we need to use to non-dimensionalize an equation cannot be arbitrary. It has to have relevance with the primary dimensions that are contained in the original equation. Very important. So for example, if the term pressure or the velocity is not playing any role in an equation, then how we can use the pressure or velocity to non-dimensionalize an equation? So the relevance has to be there. It has to be a typical representation of the equation, and then we use it in a sensible manner if we want to get sensible answers. The primary dimensions of all parameters are, and we have mentioned this before, when it is length, whether it is denoted by Z or X, or diameter D of a sphere, or radius R of a circle, it is length, and length is denoted by L, will have the dimensions of length. T, time, small t is denoted for time, and it is taken as time even for our representation. Z0, that is a typical scale, will be Z0, and that will have the same dimensions as the length L, the variable Z. So when we divide Z by Z0, the number will become dimensionless. It will have no dimension. Similarly, the velocity W, or if it is V, has the dimensions of x over t, where x is the distance divided by t is the time, and distance has the dimensions L, length, and time has the dimensions of time, so they will be denoted by W0. Typical scaling parameter for velocity will be length over time. G, representing the acceleration due to gravity, will have the same dimensions that of the normal acceleration, so it has dimensions of L over t square, sometimes also written as L into t to power minus 2. And the non-dimensionalized parameters or variables are normally denoted by giving a asterisk, as you can see here, on top of the alphabet, and that will be equal to the original variable divided by the scaling variable, and the resultant non-dimensional parameter is shown as with a asterisk sign on top of it. The same thing for time, and the same position will be there for other variables also. You can note here that for t we have also written here we have multiplied with the velocity, and the velocity will have dimensions of length over time. So that is also included there. And you can see the left hand side is t asterisk and the right hand side we have t appearing there. So the result will be this one. The main point is to make a differentiation, to make a difference between the two numbers. So if we are using t small t for time, we use t asterisk for non-dimensional time variable. Similarly, we can calculate these things for acceleration also and other terms. The acceleration is given by d2z by dt2, and this can be written as d2 by d into, now z is replaced by z naught times z asterisk. Why? Because z asterisk is equal to z over z naught. And similarly, the term t here is taken from there and we have substituted the same value. When we simplify the terms, they give us the dimensions of acceleration. And they are equal to, all of them, when we simplify them, results to -1. And you know -1 is an absolute constant, therefore having no dimensions. The ratio W naught over square root of G into Z naught is known as Froude number. Froude number is a ratio of inertial forces or momentum forces divided by gravitational forces, because they are the two that are occurring. And so we take the square root here of this. Now this Froude number is used a lot in problems that deal with open channel flow and that kind of situation. And it has been named after the researcher who first used it, Froude. In a typical fluid flow problem, the scaling parameters usually include a characteristic length L, a characteristic velocity V, and a reference pressure P naught minus P infinity. So this is a typical pressure term. They will have the same terminology, and these are the most common parameters that we come across in a fluid flow. So if fluid is flowing from the left hand side to the right hand side direction, then with a velocity V, there may be some pressure, it may be exerting some pressure over a length scale L, and so these terms are shown to be appearing here, and these are the most common things that appear. And as I say, in a fluid flow situation, Froude number is most commonly used. You can see here, and the two values that in a fluid flow is shown here in an open channel flow through a sluice gate. So a gate that can be closed and open. You can see the initial point, the velocity is V1, the height is Y1, and later on it develops into a flow whereby the velocity is V2 and the height is Y2. And you can see the Froude 1 and Froude 2 has the values as shown, and both of them are non-dimensional numbers.